It might surprise you to learn that machine learning models or language models do not consume textual data. Instead, they exclusively work on numerical data. Therefore, this textual data needs to be converted into numerical format. In this video, we are going to talk about text data preprocessing pipeline, which help us convert this textual data into numerical format called tokens. Let's quickly have a look at the different source of textual data. These are just a few examples of the many potential sources of text data. Now let us come to our main topic, text data preprocessing. Text data preprocessing in natural language processing and language models involves essential steps to transform raw textual information into a format that can be effectively understood and utilized by machine learning algorithms, which is the numerical format. This process can be broadly divided into two main phases. Number one, text to text transformation, and number two, which is text to number, which is also called encoding. Let us talk about text to text transformation. This initial phase focuses on refining and structuring the text itself for better readability and understanding. It consists of the following key steps. Number one, cleanup. The second is normalization. Then there is chunking and segmentation. Let us talk about text to number transformation. This is also called encoding. It is about converting the structured text data into numerical representation. This process includes tokenization, sequencing, and padding. We will talk about them in detail in the subsequent slides. Under text to text data preprocessing, let us talk about cleanup. So cleanup involves removing noise, irrelevant characters, and formatting inconsistencies to ensure that the text is cleaner and more conducive to analyze. Here are details about various aspects of cleanup task along with examples. Number one, handling punctuations. So what is the objective? Objective here is to eliminate non-alphabetic or non-numeric characters that don't contribute to the text meaning. Example like removing punctuations marks like periods, commas, exclamation marks, etc. from the sentences. Now handling HTML tags. Stripping HTML tags and entities that are often present in web data but are unnecessary for text analysis is important. Then dealing with URLs. Treating URLs, email addresses, or other web-specific identifiers as single entities or replacing them with a generic token is essential. Handling redundant white spaces. So here objective is to normalize spaces, tabs, or new lines to a consistent format while removing extra white spaces. Then spelling correction. Objective here is to correcting obvious typos or inconsistencies in the text if possible, or marking them for further processing. Say there are some typos in the words like hello, then it is better to make them proper, like hello with the right spelling. Removing stop words. Now, eliminating common words that occur frequently in a language but do not carry significant meaning and might hinder analysis is very important. So words like the, and, is, in, etc. are typically stop words. For instance, in the sentence, the cat sat on the mat, the stop words the and on might be removed. Handling emojis and emoticons. With more and more usage of social media platforms, there is an explosion in the usage of emojis and emoticons in our day-to-day life. Depending on the context, we can apply various methods. They are broadly classified into two. One is replacing and the other one is preventing. So depending on the use cases, we can either replace them or prevent them. So in case of use cases like sentiment analysis, The emoticons and emojis give some valuable information, and so removing them might not be a good solution. We should convert to word format so that they can be used in downstream modeling processes. And in the use cases where they do not make sense, so probably we might need to remove these emojis and emoticons for some of our textual analysis. Normalization in text data preprocessing involves standardizing text to ensure consistency and uniformity, facilitating easier analysis and comprehension by machine learning models. Here is a breakdown for normalization techniques. The first one is lower casing. Convert the input text into same casing format so that the cat, and this cat are treated the same way. Then we need to handle contractions and expansions. They're just to maintain the consistency and uniform representation of the textual data. Then removing accents and diacritics. This is just to standardize text across different language variations. Then handling numbers. Converting numbers to a consistent format is again very important to maintain the uniformity throughout the text. Then handling abbreviations and acronyms. It is always better to expand the abbreviations or acronyms to their full form to give more clarity and consistency. Normalization ensures that text data is in a consistent format, reducing variations that might not add semantic value but could cause confusion for machine learning models. By applying these normalization techniques, which we just talked about, text becomes more structured and standardized, making it easier for models to extract meaningful patterns and information during analysis and training. Under text-to-text data preprocessing, let us talk about chunking or segmentation. Generally, for real-world applications, we deal with large text corpus, which generally does not fit into the token limit of the NLM APIs. Therefore, it is necessary to split the text into chunks. In the context of building LLM-related applications, chunking is the process of breaking down large pieces of text into smaller segments. Chunking or segmentation, as simple as this sounds, there is a lot of potential complexity here. Ideally, we want to keep the semantically related pieces of text together. What semantically related means could again depend on the type of the text. Now imagine we have this text corpus and we split this text as follows. We could end up with part of the sentence in one chunk and the other part of the sentence in another chunk. And then when we are trying to answer a question like what are the use cases of LLM, we actually don't have the right information in either chunk because it is split apart. Therefore, we would not be able to answer this question correctly. So there is a lot of nuances and importance in how you split the chunk so that you get semantically related chunks together. To tackle this situation, there is something called chunk overlap. The basis of all the text splitters involves splitting chunks in a small chunk size and some chunk overlap as shown in this picture. A chunk overlap is generally kept as a little overlap between two chunks, like a sliding window as we move from one to the other. And this allows for the same piece of context to be at the end of one chunk and at the start of the other and helps create some notion of consistency. By applying an effective chunking strategy, we can ensure our search results accurately capture the essence of the user's query. If our chunks are too small or too large, it may lead to imprecise search results or missed opportunities to surface relevant content. As a rule of thumb, if the chunk of text makes sense without the surrounding context to a human, it will make sense to the language model as well. Therefore, finding the optimal chunk size for documents in the corpus is crucial to ensuring that the search results are accurate and relevant. Okay, so if you have followed till here, so now your data is cleaned, normalized, and segmented. Now, what is next? Next step is to convert this data into numerical format because as we know, ML algorithm works with numerical inputs. Therefore, we need to convert the text data into numerical format that the algorithms can understand and process. To do that, now let us talk about the end-to-end text data pre-processing pipeline. So this is a very high-level text data pre-processing pipeline where the first part is text-to-text transformation, which is the basic transformation which we so far we talked about. Also normalization, cleanup, and segmentation. And the second one, which is about text to number, which is word encoding. This is a very crucial one, an important one, which we are going to now learn about. So let us start with tokenization. Tokenization is the process of breaking down a text document or corpus into smaller units called tokens. Tokenization can be performed using different techniques, such as word level tokenization. In this case, each word is treated as one token, or character level tokenization. In this technique, each character in the text document is treated as a separate token. Or there is a third approach, which is sub-word level tokenization. In this technique, the word is broken down into sub-words, and sub-words are treated as tokens. We will learn about them in detail. Now, sequencing. Sequencing is the process of converting a text sentences into numerical vector with help of tokens. Now, padding. Padding is a technique used in text data preprocessing to ensure that all input sequences have the same length. Why? Because we are dealing with matrix manipulation, and matrix manipulation are efficient if the size of the matrices are same. So what we do in padding, it involves adding extra tokens, usually zeros, to the end or to the beginning of the shorter sequences so that they are the same length as the largest sequence in the dataset. So consider this our text corpus. It's a very small text corpus. And if this text corpus is fed into this text data preprocessing pipeline, and what we get is basically this vector. So here you see we passed this text corpus in this text data preprocessing pipeline, and what we are getting is the vectors. Let us take an example and see how this end-to-end text data preprocessing happens. Say we have our raw text corpus like this, which is a very small corpus, and we do not have much for normalization or cleanup because the data is already in a very good shape. But what we can actually do is just to do the lower casing. So change to lowercase. So we get this. Next, we will do sentence segmentation. So here corpus is broken down into sentences like this. Now we will do tokenization. In this case, we are considering each word as a token. As part of tokenization, each unique word will be assigned a unique number. So we get this. So here you see each word is assigned a unique number. Using these tokens, now sequencing will form the vector representation of each sentences. So here we get the vector representation of our individual sentences. Finally, padding will take place to ensure that all input sequences have the same length by adding 0 in the beginning. 0 can be also added to the end, but in this case, we are adding in the beginning. So this is the end-to-end example of text data preprocessing, where we can see we are doing some part of text to text transformation, and then we are doing the text to numerical transformation, which is encoding, where we are doing tokenization, sequencing, and padding. Let us learn more about tokens. Take this example. I love cats and dogs. Here each word is very common. Therefore, each word is treated as one token. So in this sentence, there are 5 tokens. Take the second example. Prompt engineering is a new domain in ML. Here, this word prompt is less frequently used word, and therefore it is broken into two words, prom and pt. Why? Because when these large language models were trained, that time this prompt engineering word or the prompt word were not frequently available on the internet, and therefore in the testing data which they have collected to train those large language models, they do not see the prompt very often, and hence until the GPT Turbo 3.5, if you do this tokenization, you will get prompt broken into prom plus pt. So therefore, you see here the prompt is taking 2 tokens, and the engineering is a new domain in ML. So they are together combining the 7 tokens, so total 9 tokens for this sentence. A helpful rule of thumb is that one token generally corresponds to about 4 characters of text for common English text. This translates to roughly 3/4 of the word. So 100 tokens will be approximately about 75 words. Different LLM models have different token limits. Token limits are defined as number of tokens in the input prompt plus number of tokens generated by the LLM in the output. Let us see some more facts about tokens. So the process of tokenization is not uniform across language. So as we talked about in our previous video, where we talked about the complexity of human language, where we talked about the diversity of human language, and we said that it is not easy to convert one language use case to other language directly. This is essentially because you see this particular sentence, what will the weather be next week? Now in English, it is taking 7 tokens, but the same sentence in Spanish is taking 8 tokens. In Korean, it is taking 12 tokens. In Burmese, it is taking 61. And in Amharic, it is taking 69, because different language has different representation of the same sentence. So it's very important to note. Let's do a quick recap. After processing, our corpus has undergone a transformation into numerical representation for sure. So we achieved till here. Each word within the corpus has been meticulously assigned a distinct numerical value, facilitating a one-to-one mapping between words and numbers. Moreover, this process extends to sentences, where each sentence is now represented as a vector composed of these tokenized numerical values. Now, visualizing this representation into n-dimensional vector space will yield a linear representation of these words like this. However, it is important to note that our current representation scheme primarily relies on a direct conversion of words to unique numerical identifiers. Beyond this fundamental mapping of words to numbers, our current approach lacks additional contextual or semantic information. While these numerical representations provide a structured foundation for analysis, they do not encapsulate deeper linguistic nuances or relationships between words beyond their individual numeric assignments. It lacks in handling those challenges of human language like ambiguity, creativity, common sense, and diversity. Okay, so what is still missing? These relationships are not yet learned, which is the missing part. That means similarities between words are not captured. Like there are similarities between dog and cat, it is not yet learned. There are similarities between dog and pet, cat and pet, dog and animal, cat and animal. So there are some relationships, the context between words. So all these are not learned yet, because so far we only transformed our text corpus into vector representation, which is just assigning a unique number to the tokens. That means the complexity in human language is not yet answered or not yet handled. Therefore, we need to move from natural language processing to natural language understanding. And this is where the embedding comes into play. So in the next video, we'll learn about embedding.